In today's lab, we will study the motion of a two-body system. First, we will use free body diagrams and Newton's second law to calculate the expected acceleration and tension. Then we will measure these quantities with different angles and counterweight masses. We will study the motion of a cart as it is pulled up an incline by a counterweight hanging over a pulley. We will use a force sensor mounted on the cart to measure the tension in the string that connects the cart and the counterweight, and a motion sensor to measure the cart's acceleration. Before taking data, let's use free body diagrams to examine the forces acting on the cart and the counterweight. Angle theta is measured between the track and the table. The forces acting on the cart are the weight, the normal force, and the tension. We will assume that the track is frictionless. We pick a coordinate system where x is parallel to the inclined plane and y is perpendicular. We will then study the acceleration of the cart in the x direction. Next, we break down the weight vector into components in these coordinates. Next, we will write down the forces that act on the counterweight parallel to the string. These include the tension and the weight. We will take the convention that forces that rotate the pulley clockwise, such as the weight of the counterweight or the tension on the cart, are positive, while forces that rotate the pulley counterclockwise are negative. Now we can write our equations for the net force acting on the cart and the weight in the direction of the string. The accelerations of these two objects must be equal as they are connected and will move together. We can then solve these two equations for the acceleration and the tension. We will use these expressions to calculate the acceleration and tension we will measure later in the lab. Using our value for the acceleration, we will also calculate the expected final velocity of the cart when the counterweight hits the floor. Now we will prepare our experimental setup in order to take data. To set up the force sensor, first connect it to channel A of the Pasco interface. Next, we will initialize the force sensor in Data Studio. Select channel A, then select Force Sensor from the menu. Then choose the Calibrate Sensors tab. We will calibrate the force sensor at 2 points. For the first point, set the counterweight on the table so the force on the sensor is 0. Then in the pop-up calibration menu, enter 0 newtons as the standard value for calibration point 1 and select Read from Sensor. For the second calibration point, let the counterweight hang free and place steel blocks on the track to keep the cart stationary. Enter the weight of the hanging masses in newtons as the standard value for calibration point 2 and then select Read from Sensor. Once you have calibrated the force sensor, elevate the track to the desired angle. Be sure that the motion sensor is tilted parallel to the track. Place a piece of tape at the point on the track where you will release the cart. You can then take the difference between this position and the position of the cart when the counterweight is on the floor to find the distance the cart traveled. Also check that the string is in the groove of the pulley and that the foam pad is below the counterweights. Let's watch what happens when we release the cart. How do the position and velocity of the cart and the tension on the string change over time? Let's take a closer look at the data we collected. The yellow region shows the time when the cart and counterweight were in motion. The start is marked by an increase in velocity of the cart, and the end is marked by the tension in the string going to 0 newtons. At this point, the counterweight has hit the floor. We can now perform fits to find the acceleration. We fit the position graph to a quadratic function and the velocity graph to a linear function. We can also use the cursor to look at values for the tension over the course of the run. We'll complete our data analysis in Excel. Enter your measurements of the cart mass, counterweight mass, and track angle for each run. Also record the distance the cart traveled during each run. Use the equations we derived earlier to calculate the expected acceleration and tension for each run. Once you have the acceleration and the distance traveled, you can also calculate the final velocity of the cart and the time it will take the weight to hit the floor. Compare your measurements to the expected values. For each angle, plot the counterweight mass versus acceleration and counterweight mass versus final velocity. Also make plots of these quantities versus angle for each counterweight. For all of your plots, include both the theoretical and experimental data. Which do you trust more, the theory or experiment?